3D trajectories are essential for studying collective fish behavior. Recovering these trajectories from video requires solving two coupled problems: spatial association and temporal association. Both problems are extra hard for fish. First, there's no 3D ground truth data for supervision. Second, every fish looks similar in shape, size and texture. Using appearance Q alone cannot separate them apart. We propose TrackFish3D, which is entirely self-supervised. It learns dense 3D tracking from calibrated camera geometry alone, without any human annotations. The core idea, for each detected fish in every camera view, is encoded using only geometric features. Then an association transformer will process all detections jointly and outputs a matrix, which is a set of probabilities indicating how likely each pair of detections from different cameras belongs to the same fish. TrackFish3D is trained with 3 self-supervised signals. The first signal is geometric pseudo-supervision. We triangulate every cross-camera detection pair and reproject it back. If the reprojection lands inside both bounding boxes, the pair is labeled 1, otherwise 0. This teaches the model cross-view association purely from geometry, with no ground truth labels. The second signal is a contrastive learning which helps cross-views association. It pulls embeddings of the same fish seen from different cameras closer together, and pushes different fish apart, shaping an identity-discriminative embedding space. Without contrastive training, same fish embeddings scatter and overlap. With it, they form tight clusters. Since fish look nearly identical, this gives the model a second cue beyond geometry, making association far more robust in dense scenes. The third signal is a temporal learning. It trains a predictor to forecast a fish's embedding from one frame to the next. So when a fish is temporarily occluded, the model can still estimate where its embedding should be and maintain its identity. Without temporal training, embeddings drift over time, causing an ID switch after an occlusion. With it, embeddings stay consistent across frames. This gives the model the ability to bridge gaps, keeping tracks stable even when fish disappear and reappear. TrackFish3D can produce an accurate identity-consistent 3D trajectory which resolve a critical bottleneck in behavioral observation. We evaluate against state-of-the-art tracking and association methods on both realistic synthetic data and real-world zebrafish footage. TrackFish3D outperforms all baselines, achieving the highest tracking accuracy while maintaining the fewest identity switches. Since TrackFish3D produces 3D trajectories, it directly enables downstream behavioral analysis. Here we demonstrate unsupervised detection of a sick fish purely from its movement, no labels needed. Using 3D trajectories, simple anomaly detectors are far more accurate than using 2D tracks from any single camera, because 3D gives you information that a single viewpoint simply cannot. Thank you for your time. We welcome any questions or feedback.